All right, this is activity 9, Newton's laws of motion. You're going to read or listen to this, and then you're going to answer some questions, and you're also going to fill in the second part of what we called the anticipation guide at the start of the activity. Sir Isaac Newton was a British scientist whose accomplishments include important discoveries about light, motion, and gravity. You may have heard the legend about how he discovered gravity when he was sitting under an apple tree and an apple fell on his head. He didn't really discover gravity, but he did realize that there's a gravitational force that constantly pulls objects toward the center of the earth. This force makes objects fall towards Earth's center if no other force is acting in the opposite direction to stop them. And the guiding question that we're going to think about as we do this reading is, what relationships between force and motion did Newton discover? And then below we just have an image of Isaac Newton, who did his work in the 1600s. This work is written in Latin. Sir Isaac Newton did some amazing work and contributed a great deal to our modern understandings. The materials, you should already have the anticipation guide glued into your notebook, and then student sheet 1.1, comparing vehicle features, is what we did at the start of this unit. Force and motion. People have always observed objects in motion and caused objects to move around. For many centuries, scientists thought they knew everything about these phenomena. In 1686, Sir Isaac Newton presented 3 laws of motion that changed how people understood these phenomena. Newton's laws were revolutionary, as they seemed to go against everyday experience and observation. Today, parts of Newton's 3 laws are the basic understanding for motion, are still the basis for understanding motion. Here you will learn about the first and second laws of motion. You will learn about the third law in a later activity. Newton's first law. Newton's first law describes an object's resistance to a change in its motion and its tendency to keep doing whatever it's doing. A change in motion can be a change in an object's speed, direction, or both. For example, a car that speeds up to pass another car or turns a corner is changing its motion. Newton's first law states that an object's motion cannot change unless a force acts on the object. In other words, it takes a force to make the object go faster, slower, or change direction. It may be surprising to you that no force is needed to keep something moving. According to Newton's first law, if something is moving at a certain speed, it will keep on moving at that speed forever. It will not slow down or stop unless something pulls or pushes on it. The idea also applies to an object that is not moving. It will remain motionless until a force acts on it. Newton's first law seems to contradict everyday experiences. You've seen for yourself, when you kick, throw, or bat a ball, it eventually stops by itself. And when you ride a sled or scooter down a hill, you don't keep going forever. You slow down and stop. How can Newton's first law be correct? There must be a force that acts on the ball and the sled or scooter. What could it be? And here we have a picture of some people sledding, and the caption says, "What makes sledding down a hill of snow so much fun?" So we're thinking about a force that acts on things to slow things down or make them stop. And now our next section is called friction. What is not stated in Newton's first law, but plays an important role in everyday motion, is friction. Friction is a force that exists at the boundary, or the place where 2 things meet, between any 2 pieces of matter that are in contact with each other. Friction opposes the motion of an object, or another way to say that is, friction works against the motion of an object. For example, the friction between a rolling ball and the ground causes the ball to slow down and stop rolling. Friction between a car's tires and the road causes the car to slow down and prevent it from sliding. For an object to keep moving in the presence of friction, a force must be applied to that object. To keep a car or other vehicle moving, its engine has to keep pushing it to overcome the friction in several places, such as the friction between the road and the tires, and between the car's body and the air. If a car's engine is pushing the car with a force equal to the force of friction, the car will move at a constant speed in a given direction. Many features on vehicles are designed to reduce friction as much as possible. The shape of a car's body is streamlined to reduce air friction. Oil and grease reduce friction between moving parts. If there's less friction to overcome, the engine doesn't need to apply as much force to move the car. Other vehicle features are designed to increase friction. Tires need to have friction so they can grab the road, and brakes need a lot of friction to stop the wheels from turning. Now we have a section called Balanced and Unbalanced Forces, and you'll see some pictures. Please pay attention to these. They have the arrows there to show the forces. When the forces on an object are balanced, the motion of an object won't change. In the figure below, the force pulling to the left is equal to the force pulling to the right, so the net force is 0 newtons. N stands for newtons, and net force means what's left over when you add all the forces together. When the forces acting on an object are unbalanced, the motion of the object changes. That is, it accelerates. Newton's second law describes the change in motion that results from unbalanced forces. Even a tiny force will cause an object to accelerate if it is not balanced by another force. In the figure below, the force pulling to the left is greater than the force pulling to the right, so the net force is 10 N, and N stands for newtons, the unit of force, and the object will accelerate to the left. Newton's second law, the relationship between force, mass, and acceleration. Unlike the first law, Newton's second law is confirmed by our everyday experiences and is easier to understand. It states that, first, to equally change the motion of two objects of different mass, more force must be applied to the more massive object. For example, when you add weight to a wagon, you have to push it harder to speed it up. 2. The bigger the force applied to an object, the greater the resulting acceleration. For example, if you give a soccer ball a soft tap with your foot, a small force over a short period of time, it doesn't speed up much. If you give it a hard kick, a larger force, over an equally short period of time, it speeds up more. Newton summed up these ideas with a single equation that shows the net force, F, needed to accelerate, A, any mass, M. So in this equation, F stands for force and the net force. A stands for acceleration and mass stands for M. And so this is an equation that we figured out in the previous activity, which we skipped over. We skipped activity 8, and the equation that Newton discovered was the force is equal to M mass times acceleration. Please take your time and do these analysis questions, and we will discuss them when I return. Thank you.